Hello everyone. Welcome back to online learning of mathematics. Last time we have learned to show the rational numbers on the number line and comparison of rational numbers. From lesson number 1, rational and irrational numbers. Some homework also was given to you, which you might have definitely completed. Thank you. Today we are going to learn decimal representation of rational numbers. In a rational number, if numerator of a rational number is divided by the denominator of a rational number, the answer which we get after dividing is the decimal representation of that rational number. For example, see here the rational number 7 upon 4. Here the numerator 7 is divided by the denominator 4 and the number obtained after division is 1.75, which is a decimal representation of the rational number 7 upon 4. These rational numbers, when converted into decimal fractions, can be both terminating or non-terminating decimals. Now, terminating decimals are those numbers which come to an end after few repetitions after decimal point. Here, see the rational number 20 upon 8. When we divide the numerator 20 by the denominator 8, the division ends. That is, we get the remainder of our division as 0, and hence it's an example of terminating rational numbers. Now, non-terminating decimals are those which keep on continuing after decimal point. That is, they go forever. They don't come to an end. Let's see this with an example. Here the number 5 is divided by the number 3. So when we divide 5 by 3 after decimal point, the number 6 is getting repeated again and again. That is, we always get the number 2 in our remainder. Our remainder never becomes 0. If a single digit or a group of digits occur repeatedly on the right of the decimal point, then that form of rational number is called recurring decimal form. As in previous example, number 6 was getting repeated again and again after decimal. So, it's an example of recurring decimal form. See these few more examples. In first example, 25 upon 9, when we divide numerator 25 by denominator 9, we will get the number 7 repeated again and again. Here, as only single digit 7 is repeated, so we will put a dot above the number 7, which means the number 7 is repeated. Now, in second example, that is minus 17 upon 11, when we divide the number 5, 4 is getting repeated again and again. As here, it's a set of numbers which are getting repeated. So, we will put a horizontal line above the number 5, 4, because this is a set of numbers which is being repeated. Whenever a single digit occurs repeatedly on the right of the decimal point, we put a point above the digit. And if a group of digits occur repeatedly, we put a horizontal line above those digits. Now, let's learn how to represent terminating decimal form to non-terminating recurring decimal form. For this, see the example below. The rational number 9 upon 4. When we divide numerator 9 by denominator 4, we will get 2.0. 25 as our answer. That is, our division will end and we will get a remainder 0. That is, it's an terminating number. So, to convert this terminating number to non-terminating form, we will add a 0 at the end and will put a dot above 0. To convert terminating decimal form to non-terminating decimal form, we have to add 0 at a end and put a dot above 0. In practice set 1.3 of your textbook, we have to write the rational number in decimal form. Let's see sum number 4, that is rational number minus 103 upon 5. When we divide we will get minus 20.6 as our answer. And the remainder here is 0. So, it's an example of terminating decimal form. In sum number 5, that is minus 11 upon 13, when we divide minus 11 by 13, after decimal, the number 8, 4, 6, 1, 5, 3 is getting repeated. So, it's an example of non-terminating recurring form. As here a set of numbers are repeated, so in the answer we have to put a horizontal line above the numbers which are repeated. Now let us learn irrational numbers. In addition to rational numbers, there are many more numbers on the number line. They are irrational numbers. For example, root 2, root 5, root 7, 3 root 2, 5 plus root 2, 7 minus root 3 and so on. Now, let us learn to show irrational number root 2 on a number line. For that, let us first draw a number line as shown. Now, mark 0 as point O and 1 as point A. In next step, draw a perpendicular at point A. Now, take a point B on the perpendicular drawn such that the distance between OA and AB should be the same. For example, if length of OA is 1 centimeters, then length of AB should also be 1 centimeter. Now join OB. You can see here a right angled triangle OAB is formed. As it is an right angled triangle, we can use Pythagoras theorem here. So, in triangle OAB, measure of angle A is equal to 90 degrees and length of OA is equal to length of AB, which means 1 unit. So, by Pythagoras theorem, length of OB square is equal to length of OA square plus length of AB square. That is, length of OB square is equal to 1 square plus 1 square, which means length of OB square is equal to 2. Now, here square of length OB is 2, but we want length of OB. So, we will take square root on both the sides. So, we will get length of OB as root 2 units. Now, with the help of compass, that is rounder, measure length of OB. That is, keep the pointer of compass at point O and tip of the pencil at point B. Then, by keeping your pointer at O, make an arc with center O and radius OB. Mark the point of intersection of the line as the arc C, which is your root 2. See the activity of practice set 1.3. Here, the point Q on the number line shows the number root 2. A line perpendicular to the number line is drawn from the point Q. Point R is at a unit distance from Q on the line. Right angle triangle ORQ is obtained by drawing segment OR. Now, length of OQ given is root 2. Length of QR is equal to 1. By Pythagoras theorem, length of OR square is equal to length of OQ square plus length of QR square. Now let us substitute the values, as the length of OQ is root 2. So there we will write down as root 2 the whole square plus 1 square. The square of root 2 is 2. Therefore, in the next step, it will be 2 square of root 2 as 2 plus square of 1 as 1. Now, the sum of 2 plus 1 is equal to 3. 3 now here is a square of length of OR, but we do not want the square of length OR. We want only the length of OR. So what we have to do? We have to take square root on both the sides. So when we take the square root on both the sides, length of OR will be equal to root 3. Now we will draw an arc with center O and radius OR. Mark the point of intersection of the line and the arc as C. The same step we will do as we have done when we were drawing root 2. The point C shows the number root 3. Next online lecture, we will learn lesson number 2, parallel lines and transversal. Thank you.